Hello and welcome to today's lecture. Today we will continue our study of algebraic sets and we will deepen the relationship between algebra and geometry by tightening the link between algebraic sets and ideals through the famous Nullstellensatz of Hilbert. And having done that, we will go on to coordinate rings of algebraic sets and take our first steps towards affine varieties. So remember that so far we have been studying affine space over an algebraically closed field, and to each ideal of polynomials we've associated an algebraic set of all points where the polynomials in this ideal vanish, the vanishing set of this ideal. So we've concluded that you can always take this to be an ideal, even if you want to study the vanishing set of an arbitrary set of functions, set of polynomials. You can take an ideal, and you can take the radical of that ideal without changing anything. This is the usual argument that if a power of a function vanishes somewhere, then the function itself will vanish somewhere. So in other words, we have looked at sets constructed as vanishing sets of radical ideals. What we want to do today is to get back the radical ideal from an algebraic set. So we want to get an inverse of this mechanism. And this is achieved to begin with by the following proposition. So take any subset of affine space and consider the ideal of this set. So this is the set of all polynomials that vanish on all points of the set. The claim is this is an ideal, this you can check, and then it's a radical ideal because if some power of a polynomial vanishes somewhere, then the polynomial itself must vanish there. And this set is called, or this ideal rather, is called the ideal of X. And sometimes we say the vanishing ideal of X. So a few remarks. The bigger you take the set, the smaller the ideal becomes. You can prove this rigorously. The main idea is that taking a larger set means that the condition of becoming zero there is stronger, so a subset of the functions will become zero there. Secondly, if you look at the vanishing ideal of the empty set, then this will be the whole ring, yeah, because there is no point. I mean, all polynomials satisfy that they vanish on all non-existing points of the empty set. And conversely, the vanishing ideal of the whole space is the zero set. There is no non-zero polynomial that can vanish on everything. If you take a point, then its vanishing ideal is this ideal generated by the coordinate functions t1 minus a1 up to tn minus an. So why is that? The inclusion is in this direction is straightforward, because if you have any of these functions, then it will vanish on this point, and so the ideal generated by them vanishes too. The inclusion in this direction, or rather the equality, follows from the following. So, okay, this ideal is now included in this ideal. But this ideal is maximal. Why is it maximal? Because when you quotient by it, so let's call this ideal J. When you quotient by J, you get the field K. This is simply taking a polynomial and replacing every ti by the corresponding ai. So this ideal is maximal, so it cannot be properly contained in this ideal. And so it is equal to it. So therefore we have an equality of ideals. To be able to claim this, I have to know that this ideal is not the whole ring, but that is easy to check. And finally, interestingly, you have the inverse relation in one direction. So if you take an algebraic set, you take the ideal of this algebraic set, and then you take the vanishing set of that ideal, you get back x. Please pause and write down the steps to why this is true by checking the mutual inclusions in both directions. Welcome back. So now you can ask what happens if we do this the other way around. If we start with an ideal, take its vanishing set, take the ideal of that set. Well, this is the content of Hilbert's Nullstellensatz. We will get to why it's called Nullstellensatz in a minute. But first, let's look at the strong Nullstellensatz. And it says simply that if you do what I said, so you start with an ideal, you take its vanishing set, you take the ideal of that, you don't get back exactly the ideal, you get its radical, which somehow philosophically is expected because you cannot distinguish between a function vanishing somewhere and the power of it vanishing somewhere. Before we prove this, what does this imply? So now we have the set of all algebraic sets and the set of all radical ideals. So we know that if we take such a radical ideal and construct its vanishing set, we get an algebraic set. And from the previous slide, we know that if we take this x and map it to the ideal of x, we get a radical ideal. The remark at the end of the previous slide says that if we compose them, so let's call this, well, this is obviously v and this is I. So if we start with I and compose with v in this direction, we get the identity. This is the last slide. And this slide says if we take I, post-compose it with v, we get the identity. Because now the ideals are radical, so this taking the radical will not change anything. And so this means that these two are inverses to each other, and therefore they are bijections, and both v and I reverse inclusions. And so the corollary follows. So this gives us a very precise link between radical ideals and algebraic sets. So we will prove the strong Nullstellensatz in a few steps. Let's start by the weak Nullstellensatz. So we will need one fact from commutative algebra that we will prove later in the course, and that actually requires some machinery to prove. So if you take any field K and you take a maximal ideal in the polynomial ring over that field in some number of variables, then you have the natural map mapping K into the scalars of this polynomial ring and then quotienting, factoring out the maximal ideal. The claim is that this is a finite field extension. Let's, for this lecture, assume that this is true, which it is. Now let's go back to our situation where our field is algebraically closed. And the claim, the weak Nullstellensatz, is that for every maximal ideal, there is a unique Nullstelle, so a unique zero place, a unique zero of this maximal ideal. So the weak Nullstellensatz says that any maximal ideal is the ideal of some point. And therefore any ideal, not necessarily maximal, since it is contained inside a maximal ideal, it will have zeros. More zeros the smaller ideal you take, but it will always have zeros. Zeros will always exist. So how do we prove this statement? Well, let us look at what we know. So consider the projection from the polynomial ring to the quotient ring by this maximal ideal. Now, according to the fact from commutative algebra, this is a field extension, a finite field extension. So it's an algebraic field extension of our algebraically closed field. So it has to be the field itself. An algebraically closed field, by definition, does not have any algebraic extensions other than itself. So this is isomorphic to the field. Now, if we call this map pi, this means that pi of t1 to pi of tn will be some element in K. So to be precise, I am using this isomorphism to map the image of each ti to the unique point in K to which it corresponds under this isomorphism. But then what will, so if we view this isomorphism as identification, then pi is evaluating at A. Because if you take pi of some ti, this will simply be ai by definition. And since pi is a ring homomorphism, it will map sums and products to sums and products, so polynomials in ti will be mapped to polynomials in ai. The value of the polynomial by definition at this point, ai. So then this precisely means that the kernel of pi is the vanishing ideal of A. A map lies in the kernel if and only if its evaluation at the point A is 0, and this is by definition means that it lies in the vanishing ideal. So this means that the kernel is this vanishing ideal, but since this is the quotient map with respect to the ideal M, this must be the kernel of pi we know is M, so these two coincide. So in other words, every maximal ideal of our polynomial ring is of this form. So we have proven the weak Nullstellensatz. And just for information, we know from before that this is the ideal generated by t1 minus a1 to tn minus an. So every maximal ideal is of this shape. As a corollary to this, we have the following result, that if you have a bunch of polynomials that do not have common zeros, then the ideal generated by them will be the whole ring itself. Why? Because if not, then this means that the ideal generated by them is contained in some maximal ideal. But all maximal ideals consists of functions that have a point, a 0 point, so this cannot be it. And since they generate the whole ring, in particular the unity of the ring is in this ideal, so there exist functions g1 to gm, so that the sum of these figi is equal to 1. Equipped with this, we can now deduce the strong Nullstellensatz from the weak Nullstellensatz. So we need to prove that we have equality between the ideal of the vanishing set of J and the radical of J. So take an ideal J. This inclusion is straightforward. Why? So how to prove that inclusion? If you have f in the radical, this implies that f of m for some number m is in J. This implies that f of m vanishes on v of j. So f vanishes on v of j, and so f is in I v of j. What we want is the other inclusion. So what we want to prove is that if we take a polynomial h, so here h is some polynomial in k t1 to tn, and if h vanishes on all points of vj, so it is in this ideal, then it is in the radical, meaning that some power of h is in j. The first step is that we may assume that h is non-zero because the statement is trivial if h is 0. Since J is an ideal of this Noetherian ring, we know that it is generated by some G1 to Gm. What we do is we add a variable. So to this polynomial ring in n variables, we add an n plus first variable, s, and consider the following polynomials, G1 through Gm, and 1 minus s times h. And I claim that they have no common zero. So what do I mean by this? Let me be precise. So I mean that the following polynomials, so g1 of t1 through tn up to gm of t1 through tn, and then 1 minus s times h of t1 through tn. There is no way to evaluate this, choose numerical values for t1 through tn and s so that it becomes 0. Why is that? Well, if that were possible, then for the t1 through tn values, all these g polynomials would vanish. But since these g polynomials generate j, this means that if we have a 0, x1 through xn, and then y, maybe, this means that x1 through xn would lie in the vanishing ideal of the whole ideal, the vanishing set of the ideal j. But then by assumption, h would vanish on that, so this part would be 0. And then whatever y is, the last polynomial will just be the constant polynomial 1 without zeros. So these polynomials have no common zero, and by the previous corollary with the roles of f and g interchanged, we can write the number 1 in this fashion. So these will generate the whole ring. So these fi will belong to this polynomial ring t1 through tn, s. All right. The next thing that we do is we specialize by setting s to 1 over h. So what does this mean? To be precise, we have a homomorphism from the polynomial ring in n plus 1 variables to the ring of rational functions, so the quotient ring of the polynomial ring in n variables, by sending all the ti to themselves, but this s we send to the rational function 1 divided by h. the effect of this is that this specialization will make this 0. So to be clear, this is a product, not an evaluation. So we're multiplying fn plus 1 by this product, which will become 0 under this specialization. And so we get 1 as a product of these fi, now with the s variable 1 over h times gi. So these fi will look like some polynomial in t1 to tn divided by some power of h. Right? Because h is itself a polynomial in the t1 to tn, so we just multiply by, put everything on a common denominator, and then we get some power of h. And since we have finitely many polynomials, we can multiply everything by a high enough power of h to clear the denominators. So then we get this equality in the polynomial ring. Now we have multiplied by a high enough power of h that these fi tilde are now polynomials, and so h to the power n is a combination of these gi, and the gi generates j, so this means that h to the power n belongs to j, so h belongs to the ideal as desired. And so from the weak Nullstellensatz we have deduced the strong Nullstellensatz. Pause and go through this proof once again if it went a bit fast. What consequences do we have? Well, as an exercise, you can check that whenever you take the ideal of a union of algebraic sets, you have the intersection of ideals of algebraic sets, while the ideal of the intersection is not necessarily directly the sum of the ideals, but it's the radical of these. So here x and x prime are algebraic sets. Under the bijection we looked at, so remember the strong Nullstellensatz implied as a corollary that there was a bijection between radical ideals and algebraic sets. Maximal ideals correspond to points. So a maximal ideal is automatically radical. Why? Because the radical of an ideal contains the ideal. So if the ideal is maximal, this has to be the same. And as we saw in the weak Nullstellensatz, the maximal ideals correspond to points under this bijection. Also, we can now make precise what we perhaps intuitively assumed, that two polynomials that define the same function on the whole affine space coincide as polynomials. So this means that if f of x is equal to g of x for all x in an, then f is equal to g. And this is because this would imply that f minus g belongs to the ideal of the whole set, which was the zero ideal. So then f is equal to g. And so this means that the affine space has enough points to distinguish all polynomials. And remember, we're working over an algebraically closed field. This would not be true over, say, a finite field. Finally, two polynomials define the same function on an algebraic set if and only if they coincide modulo the ideal of that set. So if f of x is equal to g of x for all x in x, well, this means that f is equal to g plus some h such that h vanishes on all x and x. And so this h must belong to the ideal of x. This we will take with us to the next part of the lecture, where we define coordinate rings.